Okay, so good afternoon, everyone. Um, Continuing what we were talking last Tuesday about the agitation and mixing. So we will now discuss about the mixing times of the miscible liquid. So why it is important? It is because usually in the rapid mixing, yeah, it will always takes place near the impeller. So the closer the fluid to the impeller, the rapid the mixing will be. Yeah. However, when it is quite far, so when it is farther from the impeller, so the slower mixing will occur. Yeah. Now, so to uh, ensure that the mixing in all parts of the fluids is pretty much uniform in all parts. Yeah, so we have to calculate the sufficient mixing times, yeah, to make sure that all the liquids will be uh, miscible to each other. Yeah, okay, so I will change my uh, virtual background because it is kind of disturbing me in explaining this to you. Mm, change my. Oh, now, so I will share my screen now. Yeah. Okay. So I hope that you also open your John Copper's book. Yeah. I hope it will be the fourth editions, since I don't think this mixing times of miscible liquids is available in the third edition. Yeah. Okay. So for you to understand it easier, yeah, by I will put the Genco place for edition and then my presentation side by side so that you can see. Yeah, so okay. Yeah, the second point, yeah, to measure the mixing time, or I call it TP, yeah, in buffet tank. Yeah, for agitation using plain turbine or turbine with disc or pitch turbine. So for me to say it's all types of turbine agitator. Yeah, so we can use the figure 3.4-6 and also NRE, NXNRE. Yeah. Now these two calculations, so the NRE and also the figure 3.4-6, yeah, can be used to find the FP, or it can be defined as a dimensionless mixing factor. Now, by knowing the dimensionless mixing factor, we can find the mixing times that is sufficient for us to mix all the liquids inside a vessel. Yeah. Now, these mixing times can be calculated using the equation of 3.4-16. So I will also display my spotlight. Wait. Okay, so I hope you see my spotlight. So this is the equation, yeah, that correlates the mixing times with the dimensionless mixing factor. Yeah, now this dimensionless mixing factor can be found using this figure 3.6. Yeah, so this is the FP value here in the y-axis, while for the x-axis it will be the NRE, the NX and RE. Yeah, I mean, okay, okay. Yeah, now to measure the agitation parameters after the scale up or scale down with similar time geometry, and also for turbulent flow or alpha equals to 1, yeah, for the same power per unit volume, yeah, the mixing time can be calculated using a simplified form of 3.4-17. So this equation is specifically for a similar time geometry after scale up or scale down, and then for turbulent flow, and then for the same power to unit volume, yeah, then we can use this equation, yeah, the equation of 3.4-17. Meanwhile, for the same mixing time, yeah, the same mixing time, then we can calculate the power per unit volume. Yeah. So it's another way to see. Yeah. So previously it's the same power to unit volume. Then we calculate the mixing time after scale up or scale down, yeah, by using this equation. Yeah. However, in vice versa, yeah, in the different viewpoints, in the same mixing time, yeah, with similar time geometry, turbulent flow, and after it is being scaled up or scaled down, then the power to unit volume can be calculated using this equation 3.4-18. Yeah, so make sure that you take a note on your book. Yeah, so that later when you need it, then you can just directly open that page. Yeah. Okay. Yeah, these correlations can be only used, yeah, for agitation using turbine type of agitator. Yeah, so either plain turbine, turbine with disc, or pitch turbine. Yeah, okay, so I will go to the next one. Okay, now, Miss, if I have not a turbine type of agitator, but I have a helical ribbon agitator, so what kind of equation should I use? Yeah, nah, so yeah, for a helical ribbon agitator, and then for the NX and RE less than 20, yeah, for the NRE less than 20, then we can use these two equations, yeah, 3.4-19 and 3.4-20. Yeah, what makes them different is only the agitator pitch to tank diameter ratio. Yeah, so if the agitator pitch to tank diameter ratio equals to 1, then you can use this N times Tp equals to 126. And here, yeah, refers to, yeah, the revolutional speed, yeah, or the rotational speed. Yeah, of course, it's in revolution per second. Yeah. Meanwhile, for the agitator pitch to tank diameter equals to 0.5, then you use this equations, the one in the below, yeah, in the bottom of the page. Yeah, N times Tp equals to 90. Yeah. Now, and then there are two notes here. Yeah, for a very viscous liquid. Yeah, the TF, so the mixing time for helical ribbon, it would be lower than the mixing times for the turbine, yeah, in the same power to unit volume. Yeah, in the same power to unit volume. Yeah, for a very viscous liquid, then the TP for helical ribbon would be lower, yeah, or shorter than the TP for the turbine type of agitator. Nah, meanwhile, for non-viscous liquid, yeah, the TT, yeah, or the mixing times for helical ribbon will be higher or will be longer than the TT for turbine type of agitator for the same power to unit volume. Yeah. Okay, so since I will upload this video to YouTube, so later if you have any questions, then you can just ask directly in the comment section below. Okay, now and then we will go to the example 3.4-4. So I will scroll it down. Okay, yeah, here. Okay, I will do it in. Okay, so using the existing conditions for turbine with a disk, yeah, in example 3.4-1 part A. Yeah, okay, so we have to find the mixing time. And then the mixing times after it is scaled down, so in a smaller vessel, yeah, and then in the same power per unit volume. And then for the third point, yeah, we also asked to calculate the new power per unit volume if we have the same mixing time after the scale is decreased, yeah, after it is scaled down, yeah, after the vessel is scaled down. Oh, sorry. No, 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 no. For the third point, we are asked to calculate the new power per unit volume if we scale it up. Yeah, if we scale the vessel up to a larger one. Yeah, but using the same mixing time as the smaller vessel. Yeah. Okay. So for the first calculation, yeah, is for us to calculate the mixing time. Yeah, with the vessel as mentioned in the example 3.4-1. The second one, if we have the same power to unit volume ratio, yeah, and then we scale the vessel down to a smaller vessel, yeah, we are asked to calculate the mixing time. Yeah, meanwhile, using the mixing time found in the second point, yeah, we are asked to calculate the new power per unit volume for the larger vessel if we scale it up now. Yeah, okay. So we go to the part A first. Yeah, so in part A, yeah, we know from the example of 3.4-1 that dP equals to 1.83, dA equals to 0.61, and then dP equals to its height. Yeah, so it's also 1.83, and then M is 90 revolution per minute or 1.5 revolution per second. And then we also know the density, the viscosity, yeah, and then we know from the example 3.4-1 that the power number, it would be the 5, yeah, here 5. And then the power required is 1.324 kilowatts, yeah. Okay, so first, yeah, to calculate the mixing time, yeah, sorry, to calculate the mixing time, yeah, we have to find the power per unit volume. Yeah, to calculate the mixing time, we have to calculate the power per unit volume. Okay. Wait, let me check. Did they ask Oh, okay. Yeah. Sorry. So it is actually required later. Yeah. So this volume will be required later. Yeah. In the second point. Yeah. So P per V1, yeah, is needed later for completing point B. Yeah. So if we are asked only to find the mixing time, then we can try to find the n accent RE. Yeah. Okay. The n accent RE can be found directly from the example 3.4-1. Let me also check. Okay, so it is known from the previous example that the n accent RE is 5.185 times 10 to the power of 4. Okay, now by using the previous n accent RE, then we can use the figure 3.4-6, yeah, to find this dimensionless mixing factor or FP. Yeah, also we know that it's 4. Yeah, now by knowing the FP equals to 4, then we can put them in the equation of 3.4-16. Yeah, so FP equals to PP times blah blah blah. Yeah, now so we put the known value of FP here for, and then PP is the one that we are looking for, and then M, yeah, we know from the previous example, the A, G, the A, H, the P, yeah, all comes from the previous example 3.4. Okay, so finally we can find PP. Yeah, so if we are asked only to find the mixing times, then actually we don't need to find this volume and P per V. Yeah, however, since point B mentioned, yeah, let me let's scroll it up. Yeah, in point B, yeah, they ask what is the mixing time for a smaller vessel? Yeah, and do this for the same power per unit volume as used in part A, as used in part number 1. Yeah, so that's why, yeah, Bianco please finally calculate V1. Yeah, it's the volume of the cylinder. Yeah, the original one. It's 4.8 cubic meter. And then we know the power from the equation of 3 point, sorry, not from the equation, from the example of 3.4-1. Yeah, we know the power is 1.3. So dividing the pressure with the volume, then we can find 0.2751 kilowatt per cubic meter. So this is the power per unit volume that we want to use in point B. Okay, now then, yeah, for point B, yeah, we have to scale down, yeah, because the volume be smaller, yeah. So by using the equations 3.48, yeah, we can find the ratio, yeah. Okay, so the tank, yeah, the smaller tank have a diameter of 0.3 instead of 1.83. Yeah, so it's actually only 16% out of 100. Yeah, out of the original one, it's only 16% in volume. Yeah, so finally we know the ratio. After we know the ratio, then we can convert all of the uh, geometry of the or the dimension of the original tank. We can calculate it. We can calculate using the ratio to find the new geometry or the new dimension of the tank. Yeah. Okay. And then if we go down, yeah. Okay. So yeah. Now, and then we know that the M accent RE is higher than 10,000, right? So it's in the turbulent region. Yeah, since it's in the turbulent region, and then the tank geometry is similar, yeah, to the original one. And then it also has another restriction, which is the same to power, sorry, same power to unit volume ratio. So we can use the equations 3.417 to find the new mixing heat. Yeah. So here, yeah, we can find this. Okay, so Tt at the second condition over Tt at the first condition equals to dA2 per dA1 in the power of 11 to 18. So we know from the previous page, yeah, by using the R, we can find the new geometry, yeah, or the new dimension of the tank, right? So we know the new dA, yeah, which is 0.1. So I put zero point 0.1 here. I put the original diameter of the agitator here, yeah, and then I put the TP1, yeah, which is 17.3 from the first question, yeah. Then we can find the TP at the second condition. Okay. So it's 5.73 seconds. Yeah. Okay, so for a smaller tank, yeah, it turns out that the mixing time will be shorter, yeah, than the original one, yeah, for the same power per unit volume. Okay, and then now we move to the third part, or part C, using the same mixing time as the smaller vessel. So it's 5.73. We are asked to calculate what is the new power to unit volume ratio. Yeah. Now, so again, yeah, it is uh, the same. Yeah, it is scaled down. Yeah, it is scaled. Sorry, scaled up back. Yeah, it is scaled up back to the original one. Yes, of course with the similar geometry. And then we know that the NRE accent it is the turbulent in the turbulent region, right? And then the same mixing time, we are asked to calculate the power to unit volume ratio. So we can use this 3.4-18. Yeah, we can use these equations, which is this one. Yeah, the one that I pinpoint right now is, yeah. So again, yeah, I know the new agitator diameter, which is 0.1, and then this is the original one, is 0.61, and then we put it inside the bracket, and then we put the P over V at the, sorry, P over V, wait, oh yeah, P over V, yeah. See, it's, yeah, correct. Yeah, it is 0.2751. Yeah, because from point B, yeah, because from point B, maybe some of you will question this to me. P per V equals to 0.2751. It is actually from the point A, right? Yeah, it comes from the original vessel. Yeah, it's not from point B. Yeah. Maybe some of you will question this, but the answer is no. Yeah. Because actually in point B, we also use the same P per V. Yeah. Okay, so I will scroll it up again. Yeah, we read again the question for point B. Calculate the mixing times and do this for the same power per unit volume as used in part A. So actually, yeah, the mixing times 5.73 that we found in point B, yeah, it actually has a power per unit volume of 0.2751. Yeah, so that's why I also can say that P per V at the second condition or at the smaller uh, vessel, yeah, it's also equals to 0.2751. Yeah, because it's in the same mixing time as the point B. Since it has the same mixing time as point B, so the power and the power to volume ratio, yeah, it will also come from the point B, which is 0.2751. Yeah, for the second condition or for the smaller vessel. Yeah. Now, and then we are asked calculate the new one P per V. Yeah, the original one if we have the same mixing time. Okay. So solving the equation above, then we can find this. Yeah, P per V at the original uh, tank, but with the very short mixing time. Yeah, it's 39.73. Yeah, it's 39. Yeah. Okay. Now, Miss, then in point A you use 0.2751 also, right? Yeah, but this is for the mixing time of 17.3 seconds. Yeah. Meanwhile, in point C, yeah, it's for the same mixing time as point B, so it's a very short mixing time. Yeah, it's 5.73 only. Yeah, so of course it will require higher P per V. Yeah, that's why the P per V resulted in this part. Yeah, it is pretty much higher. Yeah, it's very much higher. Yeah, compared to point A. Yeah. Okay. Okay. So the logic is for the original one, if we use the same power as the original one, yeah. If we have the original tank and then we scale it down to a small tank, and then we use the same power to unit volume ratio, yeah, of course, then the mixing tank, the mixing time, yeah, it will be reduced, yeah, because it used the same power, yeah, the same power, but for a smaller volume, yeah, so it will require shorter time, yeah. Now, however, if we scale this smaller tank back to the original one, but I still use the same mixing time, yeah, as the smaller one, then of course this system, yeah, needs a higher power, yeah, to ensure that all liquids will be mixed well, yeah. That's why the P per V is very much higher as compared to the point A, yeah. So P per V we find in point C will be uh, higher than the P per V we found at point A. Yeah. Okay. Okay. Now, so we know that the agitator works like a centrifugal pump, impeller. Yeah, so if we try to go back to the pump and gas moving machine, yeah, we learn that the centrifugal pumps has an impeller, yeah, installed inside the casing, yeah, and the impeller will rotate and move the fluid inside. Yeah, it moves the fluid inside. Okay, now so the agitator actually works like that as well. Yeah, like that kind of pump impeller. Yeah, and it also gives the flow. Yeah, it will give the flow a pressure head. Yeah, now and then when the fluid mix inside the tank, it will also circulate, right? Yeah. So the fluid will circulate inside the tank. Yeah, it will like, it will go from this point to this and rotate, go back to the original point, and then again rotate for another rotation. Yeah. Now, so the circulation rate of the fluid, yeah, caused by the agitation, yeah, is usually calculated by the approx method using a dimensionless flow number or NQ. Yeah. Okay. So I will put it down here. Okay. Now, yeah. Now NQ itself can be calculated by using the equation of 3.4-21, which is this one. Yeah. So NQ equals to Q over M times A to the power of 3. Yeah. So this is when we want to find the dimensionless flow number or NQ. Yeah. Nah, nah. This NQ can be also used to find the circulation rate of fluid or Q. Yeah. So yeah. The point here is by using the NQ value, yeah, we can find the circulation rate. Yeah. So what is the volume of the fluid that circulates along with the tank wall? Yeah. It's the one that we want to know from this equation. So this Q is the one that we are looking for. Yeah. Now the NQ itself, yeah, equals to 0.5, yeah, for the marine propeller when its pitch equals to its diameter. Yeah. And then NQ will also equals to 0.5 if we use the impeller of 6-blade turbine with disk, when its W over the A ratio equals to 1/8. Yeah. And then NQ equals to 0.75, yeah, for 6-blade turbine with this, when the W over the A ratio is 1/5. And then pitch blade turbine when the W over the A equals to 1/5. Yeah. Okay, so by knowing this NQ value, we put it here. We know the rotation of the impeller. We know the diameter of the agitator. Then we will know the circulation rate of the fluid. Yeah, so what is the volume, yeah, of the fluid per unit time that circulate along with the tank wall? Yeah, along parallel with the tank wall. Yeah. Okay. If you have any questions, then you can put it down in the comment section. Yeah, I will answer it as soon as I open my YouTube. Yeah. Then before we go to the next subchapter, yeah, there are assignments for you to do. Yeah, for this agitation and mixing subchapter. Yeah. So the first assignment is in the previous slide here. Nah, this one. Yeah. In the slide of agitators go up and down. Yeah. So I want you to derive the equations of 3.4-12. Let me scroll it up. Oh, oh, wait. This one, yeah, yeah. From this, yeah, derive it to this, yeah. Use any mathematical means, yeah, for you to derive this to this, yeah. So that's the first problem that you have to solve, okay. And then the next one, it would be the problem of 3.4-2, 3.4-4, and 3.4-9 function boxes. Yeah, so for this subchapter, there are 4 problems that you have to solve. Yeah, okay. Now I will go to the next subchapter, yeah, about the spatial agitation system. Yeah, so the spatial agitation system can be divided into several examples. Yeah, so the first one is the suspension of solid in liquids. Yeah, so this is where the mixing is required to keep the suspended solid to be dispersed or fluidized uniformly in the liquid. Yeah, so like a fluidized bed. Yeah. Okay, now so it usually uses pressurized gas as the mechanical force for the mixing. Yeah. Okay. Yeah. Okay. So sometimes there will be like a sparger. Yeah. So there is one agitator and there's also sparger. Yeah. The gas that used in the sparger is the pressurized gas. Yeah. That to make the solid. Yeah, which usually has higher density and stay in the bottom if we do not do anything. Yeah, but after we after we do the sparging, yeah, and then also do the mixing, then we hope that it can make the solids, yeah, make the solids fluidize uniformly inside the tank. And then the second one, yeah, is the dispersion of gases and liquids inside the liquids. Yeah. So this is where mixing is required to chops, yeah, to make the bubble, become very small, yeah, into a very fine bubbles, and then make it disperse uniformly, yeah, in the liquids. Yeah. Nah. So sometimes, yeah, that's why it's called spatial agitation system because in the plate, yeah, yeah, in the plate there will be like a perforated holes, yeah, a perforated. So the blade of the turbines, yeah, it will be perforated, yeah, yeah. Kalau nggak tahu perforated itu berlubang. So there are a lot of holes there, small holes, yeah, and then that's where the bubbles comes into the liquid, yeah. So that's why if we use this type of agitator, yeah, the bubbles will go up like this, yeah, during the agitation. Yeah. Okay. And then, yeah, the third one is the motionless or static mixer. Yeah, so actually mixer, yeah, it doesn't always go with an agitator. No, yeah. So sometimes we have a mixer, but there is no agitator. Yeah, we call it as a motionless mixer or static mixer. Yeah, so there is no moving part at all. Yeah, so no moving impeller. Yeah, no moving agitator. Yeah, but there is a stationary element attached inside the mixer. Yeah, so there is a stationary element. Yeah, so later when you open the video here, yeah, I put the YouTube link here, for you to see, yeah, how this motionless mixer mix the liquids. Yeah, okay. So yeah, this element, usually placed like a helix or like a screw or in other twisted shape. Yeah. So when the fluid passed, yeah, that route, yeah, it will make the fluid to blend when the two liquids, yeah, or the two fluids comes together, yeah, and then it has an impact with the element inside the mixer, then it will start to mix and blend. Yeah, you can see directly in this YouTube link. Yeah. Okay, so that's the third spatial agitation system. Now, and then the fourth one, it will be the powder mixer. Yeah, so it's used to mix solid components. Yeah, so one example is the double cone mixer. Yeah, so if you know how we mix cement. Yeah, how we mix cement. Yeah, yeah, it looks like that. Yeah, so it's like we if we want to mix powder and powder, yeah, we use the double cone mixer. Yeah, and then the last one, it will be the paste mixer. Yeah, so this is usually used for bakery. Yeah, I told you last time in the class. Yeah, so the components inside, yeah, it's required, yeah, to be divided, folded, and then recombined. It's just like when you knead the cake, when you knead the dough, yeah, to make the bread or cake. Yeah. So therefore, since we have to divide, fold it, recombine, divide again, and so on, therefore the blade is usually, the shape is usually like a twisted ribbon, yeah, like a spiral, yeah, like a helix, yeah, like this. Yeah, it can be horizontal, it can be vertical, yeah. It depends on the size of the tank. Yeah, usually if you have only like a home industry, usually they will use not the vertical one because it is kind of difficult for us to take it from the top. Yeah, so usually they will use the horizontal mixer. Yeah, so it's easier, yeah, for the personnel to take out the dough after the kneading part, after the kneading procedures. Yeah. Okay. Okay. If you have any questions, yeah, then uh, if you have any questions, then you can place them in the comments below. Yeah, in later. Yeah, when I open my YouTube, then I will just directly answer for you. Okay. If you don't have any questions, then uh, okay. So I think okay. If you don't have any questions, then you can work on the first and second assignment. Yeah, and then submit the answer. Yeah, not to my locker. Yeah, but to Bella. Yeah, because this is weekend. Yeah, I don't think that you can collect or submit it to my locker. Yeah, because the administration office will be closed. Yeah, during the weekend. So upload it to Bella. Yeah, the deadline not April 21. Yeah, it should be April 24. Yeah, April 24 or tomorrow. Yeah, the latest is the same. Yeah, at 12 p.m. Yeah, at 12 p.m. Yeah, and then after giving it some thought, yeah, for the subchapter 3.5, yeah, I will explain it directly to you on the Monday class. Yeah, because I think I still have time to finish chapter 14 in the next uh meetings. Yeah. So after some, after I give some thoughts, yeah, and then calculate the time whether I can finish chapter 14 in the last, you know, 6, 7 meetings, then I decided that, oh yeah, it still can fit, yeah, to the next meetings. So I decided that for subchapter 3.5, I will directly explain it to you in the class on Monday. Yeah, so I will just finish the subchapter 3.4 this time, yeah, and then give to you the assignment, yeah, for you to work on, and then the assignment will be collected tomorrow, yeah, to Bella. The latest will be 12 p.m. Yeah, in the afternoon. Okay, and then we will meet again on Monday at 10:40 sharp. Okay, Thank you very much and have a good weekend. Don't forget to do your assignment. Thank you very much.